Hello again. This is part 2 of the April 14th remote delivery for 2115. We have begun talking about trees, and it turns out trees are important in syntax, and that in fact is found in compiler design. We'll say a little bit more about that later, but this is how we can test the syntax or we develop parsed trees. Just to give you an example, here is a small subset of English grammar that specifies what a sentence is. It's a noun phrase followed by a verb phrase. A noun phrase can be an article and then a noun. A noun phrase can be writing an article, then an adjective, then a noun. A verb phrase is a verb, and so on and so forth. We've got articles, adjectives, verbs, and nouns. So those are the elements of the grammar that we have so far. Now, some computer scientists, Backus and then later Nauer, and actually I'm not remembering which one came first, did develop this kind of notation. And in this notation, they wanted to symbolize what was going on in those previous statements. So a sentence is going to be a noun phrase followed by a verb phrase. This is what a noun phrase is, this is what a verb phrase is, and so on and so forth. So this is called the Backus-Nauer notation, and we'll talk about this a little bit when we're talking about grammar later in the course, where we're going to be talking about computer syntax grammar. But if we had a sentence that was called then, the young man caught the ball, this is in fact the representation that it would have. You have a noun phrase and a verb phrase, but you have all these parts of speech, but they fit together in the right way and it becomes a sentence. So this is a legitimate sentence. And again, if you look at this and think about this, oh, the structure is a tree. Arthur Cayley, a great mathematician, enumerated all isomers for certain hydrocarbons, and he used graph theory to do this. Hydrocarbon molecules are composed of carbon and hydrogen. Each carbon atom can form up to 4 chemical bonds with other atoms, and each hydrogen atom can form 1 bond with another. Thus, the structure of a hydrocarbon molecule can be represented by graphs such as those shown here. And we've got H's and C's representing the molecules of carbon and that. Now, the thing for you to notice is that both this side and this side are C4H10, but they are different because the bonds are different. So this is butane, this is isobutene, and things that have the same chemical signature but different bonds are called isomers. An isomer is saturated if it contains the maximum number of everything is connected. You can't add anything more to it. And so these contain the maximum number of hydrogen atoms for a given number of carbon atoms. Cayley showed that if a saturated hydrocarbon molecule has K carbon atoms, then it has 2 times K plus 2 hydrogen atoms. And I am going to point you to the second piece of this proof, but the first step he had to do in order to do this was prove that the graph is a tree. And so we're going to prove this, and we're going to talk about this by contradiction. So suppose there is a hydrocarbon molecule that contains the maximum number of hydrogen atoms for the number of its carbon atoms, and the graph is not a tree. So we're assuming this and the negative, and we must derive a contradiction. So since G is not a tree, G is not connected, or G has a circuit. But the graph of any molecule is connected, so G must have a non-trivial circuit. So now we're going to look at the circuit that G must have. So the edges of a circuit can link only carbon atoms because every vertex of a circuit has degree at least 2, and a hydrogen atom vertex has degree 1. That has to do with its chemical properties. So we can delete one edge of the circuit. And so, for example, this is the circuit that would exist. We can delete an edge, which has to have carbons on either side, and we can add then, to keep it saturated, 2 hydrogens. but the resulting molecule has 2 more hydrogen atoms than the given molecule, and the carbons have been unchanged. This contradicts the assumption that the given molecule had the maximum number of hydrogen atoms for the given number of carbon atoms. Hence, the supposition is false, so G must be a tree. We'll say more about that later, but this is the end of part 2.